Greetings everyone and welcome back to the bench. On the bench today is a stereo LM3886 power amplifier board. This is the last of the 4 boards that were sent in to me for review. This was sent in back in the springtime and now it's late August. So I'm finally getting around to it. Better late than never, right? Well, I have a lot to talk about with this board, so get started right away. Still in the shrink wrap, we have looks like a couple screws, 3 screws. Must have given us an extra one. I think they're for mounting the amplifier chips to a heat sink. Up front here I see a full wave bridge rectifier. So you have to use a center tap transformer with 26 volts from the center tap to either outer side of the coil. You can use a lower voltage transformer if you can't find that, but I wouldn't go any higher. Then it goes through these large 10,000 microfarad Rubicon caps. I don't know if they're authentic, but the board, I think it costs around $30, so it might be okay. And looking at the traces here, the power supply continues on over here. Looks like a couple 12 or 15 volt regulators for these chips, since they can't handle the full voltage that actually goes to the power amp. So we have some more smaller electrolytics. We have some film capacitors. Looks like it's a pretty nice power supply section on the board. As far as each channel, you see pretty much split this down the middle, and each side is the same. You have your input capacitor using these WEMA capacitors, these film caps. Each op amp here is NE5532, so there's 2 op amps in each IC, and they appear to be using both. And it comes out to this jumper. I'm not sure what that does. I think it skips over one of the op amps. I'll have to look at that. And I have another large cap. It goes in. I'll look at this side because stuff's in the way there. And we have the circuitry for the power amplifier. Looks like they're using decent screw terminals for the supply and outputs. And I'm not really crazy about these terminals, but these are just for the input. A couple issues I see with this board already. I don't see an output teal network, which is an inductor in parallel with a resistor, which helps the amp deal with high capacitive reactance loads on its output. Also in the feedback network there's usually a small value cap and resistor, which helps to compensate the amp. Another issue I see, this is the supply rail. This is, it looks like the negative rail right here. It runs all the way over to this power pin. Pretty long trace before it gets over to this chip, and there's no other film caps going from the amp to the ground that I can see, or from the supply to ground near the chip that I can see. And when I designed my JAT501 amp, I had that issue with the long supply traces, and I was getting oscillation in the output stage. So like I always say, I really like to see power supply bypass film capacitors or good ceramic capacitors very near the chip, which of course bypass the supply rail to ground. So that's a pretty good distance there. Of course, this rail being close to the chip, it doesn't have that far to travel. So it's still, it'd be nice to see a film cap going from here to ground very close to that chip. Opposite issue on the other chip. Of course, this rail is pretty close to that power pin, but this side, it runs on the top side of the board, jumps through here, and then comes over to the power pin for the positive rail. So it has to travel a decent amount of distance. Well, I guess what I'm getting at is, will we see stability issues with this amplifier? And we'll put it to the test. Well, I cracked the shrink wrap and there's already a problem. I noticed something was shaking, and look at that. This capacitor is broken loose. I can feel that. I don't know if it shows, but when I move that I can feel that these are loose. The solder connection. So I'm going to go around and inspect this board and fix the soldering here. And while I'm waiting for the soldering iron to warm up, we'll have our Snickers moment here. Enjoying himself, taking a little nap in the sunlight, being lazy. Yeah. No, I woke him up now. Well, the plot thickens. I sucked off the solder and put my own planet-killing lead-based solder on this capacitors, and I reflowed these larger components. And it did firm up the capacitor. It wasn't shaking anymore, but when I started shaking the board, I heard something rattling still. And it turns out this capacitor, it's rattling. Let's see if I can get a measurement off of this thing here. So I use this meter. I think it can measure large value caps. Yeah, they're about what they should be. I don't think a real Rubicon would do that. Yeah, this is this is a little weird. And I put the capacitor back in. It holds a charge. It measures okay. Seems to be doing its capacitor thing. But I am interested in investigating these after the video, or after the tests at least. This is not a heatsink. It's just a heat spreader. Being 60 or 70 watts per channel, you would need a large heatsink with fins. So I drilled, tapped, and deburred heatsink compound. Cut screws down to size so they don't go all the way through. And that'll allow me to clamp something larger, like this big thing here. That should work. If you actually build the amplifier, you want to use L brackets on the heatsink. You don't want this thing flopping around in the breeze, flexing the pins. You need something substantial to, hold it steady. A good mechanical connection there. Okay, have everything hooked up. One thing I didn't like, see how flimsy those are? They had the screws down so tight, almost ripped the connector off the board. They're very flimsy as I'm tightening the screws down to clamp onto the wires. But anyway, I have the power supply set up so I can have dual rails. I could go in through the AC connector, but because of this full wave bridge rectifier, there will be two diodes in series, causing about a 1.4 volt drop. So what I did is connect the supply right to the DC rails of the amp, so I won't have that voltage drop. So what I'll do now is turn on some music and give you a sample. Okay, here we go with some YouTube safe music. Sounds pretty good. I'm not hearing a lot of hiss. There is a little bit of hiss, but that's from the preamp. But it's pretty quiet amp otherwise. I did notice you have two little rail indicating LEDs for, to show that each rail is operating. That's kind of nice. Okay, power test time. I got the big heatsink clampulated on here. Only going to drive one channel. The reason being is it's a regulated supply, so it wouldn't make a difference. However, my supply is limited to 3.2 amps, and I'll run into issues if I try to drive both channels. So I have the 8 ohm resistor here on this heatsink. Since we're going to develop a lot of current, hopefully it dissipates enough heat and I don't melt my little clip. And well, we'll get you pointed at the scope. Okay, so the first test is, like I say, 8 ohms with the supply at as high as I can take it, plus or minus 32 volts. And there we go. And you got a little notch there with the clipping. Maybe something with stability going on there. But I just have to tune that out. And we're getting 20.54 volts RMS. 20.54 squared divided by 8. 52.7 watts. So we are indeed doing pretty good. I got all the power measurements done for an 8 ohm loads. I usually save this for the end of the video, but I go ahead and do it now. And look at this, at 4 ohms plus or minus 32 volt supply, we hit 90.44 watts. That's great. However, I wouldn't push that chip so hard. I would run it with 4 ohm loads to a maximum of plus or minus 28 volt rails, which gave us a very decent 72 watts. At 8 ohm loads, I was able to get 52.74, and like I said, I can't go all the way up to plus or minus 35 volts, but I would expect you would get around 65 watts. So that is excellent. But if you wanted to run it at lower supply voltages, I took these measurements as well. Here is one issue I'm having with the amplifier, mainly with 4 ohm loads. It's oscillating right at the clipping point. We're getting that notch. It was on the top with the 8 ohm loads, but I had the clips reversed on the 8 ohm loads. This is the way it should be. But at the clipping point, there is instability going on. And that's due to several factors. Like I say, it doesn't have the output teal network. It doesn't have the compensation and the feedback. And it also has that issue with the supply decoupling not being close enough to the IC itself. If those were corrected, I would expect you would not have any of those issues with this amplifier. Okay, it's time to do the frequency response test. So I have the Field Tech function generator hooked up. We're at 1 kilohertz. This peak will be at this graticule, this peak at this one, and we'll see how it deviates from that during the test. Now you can see a little waveform on there. I saw the same thing with the other amp I tested in the previous video. That's just some noise getting in there. I can't really do anything about that. So for now, let's take the signal down to a very low value. We'll take it down to 10 hertz. So we're about 2/3 of what we were. So let's turn that up. This is 20 hertz, so it is off slightly. I mean, it's not very bad at all. We're practically there. The reason for that is the capacitors they use. They could have used a higher value. They use these 1.5 microfarads. I would have gone with 2.2s or 3.3s maybe, if you wanted to get the flattest response down to 20 hertz. To me, this is, you would never hear that difference. But at any rate, let's take it all the way up to 20 kilohertz. Okay, that's 20 kilohertz. It's flat, perfectly flat. And like I usually do, we'll take it up higher. Okay, we took it out to 100 kilohertz and it's still flat. No problem with frequency response. Okay, we'll take a look at distortion. Like I say, with these 8-bit scopes, you really don't have resolution to see hi-fi performance amplifiers distortion levels. But, you know, if something gross stands out, still want to be able to flesh it out here. As usual, the 1 kilohertz fundamental, 4.5 kilohertz pilot signal. That's at 1% of the fundamental, which again just allows me to compare the harmonic nodes, see how much distortion there is. And we're looking at a pretty good amplifier. There might be a little node here bouncing around a little bit. I think there's some noise getting in. Sometimes the little nodes could be from the scope itself, but I think the amplifier is doing pretty good here. I am measuring at a 4 ohm load. It'd be really difficult to see any distortion with an 8 ohm load. And even with a 4 ohm load, I shouldn't be able to see anything with a hi-fi type amplifier. So go ahead and move on to 10 kilohertz. 10 kilohertz is looking good. I don't have a pilot signal in there because it'd have to be at 45 kilohertz, and that's beyond my ability with this music player to put a pilot signal in. There's a little blip of a second order harmonic, but otherwise it's very clean. Now we're at 20 hertz, and yeah, it's a very clean amplifier. You know, if I had better equipment, I could test this a little better, but I don't think you'll have any issues with distortion. Okay, for the final test is the step response test. And this will kind of flesh out any instabilities with the amplifier. What a step response test is, you put in a square wave into the amplifier. You want to remove any low pass filters on the input. This amplifier has a 100 picofarad disc capacitor on the input to help filter out RF, but I'm not going to take that out. I'm not going to go to that level. Plus the signal has to pass through the preamp and all that before it gets to the power amp. But yeah, I'm not going to monkey around with it. And, you know, this is a pretty involved test. You have to test it at different loads, different supply voltage, different signal levels. For stability test with capacitors added to the output, you have to try different values. Very, very involved test, but it does flesh out instabilities with the amplifier. Okay, so I'll turn on the field tech. I also should mention that this can be a very strenuous test because you're putting in a square wave and it's not going to be all the way at clipping level. So the amplifier and your load will dissipate quite a bit of energy, so just be aware of that. Okay, so I'll turn on the field tech. And that's 10 kilohertz signal with a 4 ohm load. Nice looking signal, very vertical looking edges to that. I'm not going to worry about slew rate and all that stuff. I'm just going to put these film capacitors across the output and see if the amp remains stable. So this is just a 2.2 nanofarad, and as usual I never see any difference with those. Next will be a 100 nano. Let's see if that does anything. Yep, see that? It's breaking out into oscillation. A small oscillation, some ringing. Let's turn that up so we can see it better. And we're getting some ringing, small oscillation. As I expected, this amplifier does have stability issues. And next is a 270 nanofarad. Now you remember when I designed the JAT501 amplifier, didn't want to see any oscillations. Yeah, you'll get some ringing, that's really all you should see, but if it's breaking out into oscillation, then there's a stability issue. Yeah, this thing broke out into oscillation there, so definite issue with this amplifier. So like I said before, this board is missing a lot of stability components. There's no teal network on the output, no feedback compensation, which I usually see with this chip, and as issue the distance of the power supply traces from the chip to the bypass capacitor. There really needs to be one close to the chip. Okay, so to conclude with this amplifier, I'm seeing very good things and I'm seeing very bad things. No issues with distortion. Frequency response is pretty flat. Very low noise. Yeah, it should be a very good hi-fi amplifier, but this implementation has issues, and I'm not sure about some of these components. I'm sure the chips are authentic because I wouldn't be getting those high power output ratings when they use fake chips, or they would have self-destructed at some point. I'm not sure about these capacitors. The video is running long. I'm not going to mess with them anymore at this point. And like I just covered on the bad side, it has the stability issues. You saw that little notch in the clipping, a little bit of oscillation in the clipping, and it pretty much failed the step response test. Though if it was stable, I mean, the square wave looks pretty nice otherwise. But breaking out into oscillation, you know, it could destroy your tweeters if you happen to have this thing in use. And the amplifier had enough capacitance across its outputs that, you know, it would break out into oscillation and potentially damage your speakers. So I'm going to call this a fail. You know, it's got to be more stable. It needs to be fixed before I could recommend this amplifier. Well, that's it. Thanks for watching.